Hello everyone. Today we begin our lecture playlist on infinite series. This is often a hard and unintuitive topic for most students, and through this playlist I hope we can change that. In this lecture we begin by discussing what it means for a series to converge. Here is an infinite series. If it looks scary to you, let's first start by breaking it down into its components. The main component of a series is its a sub n term, which is what we call a sequence. Simply put, a sequence is just a list of numbers. These lists can contain anything. They can contain fractions, irrational numbers like e and pi, or integers. They can sometimes follow a very nice pattern, and other times they don't really have to. We represent sequences with the notation a sub n, where n is the indexing for the terms in the sequence. So for this sequence, for instance, 1 is the term a sub 1, 2 is the term a sub 2, and 3 is the term a sub 3, and so on and so forth. Now let's look at what a series is. If a sequence is just a list of numbers, a series is the sum of those lists of numbers. Now, let's finally define what it means for a series to converge. We say that an infinite series converges if the infinite sum is equal to some finite number L. In more formal terms, if we look at the partial sum, or a sum to some finite number n, then the convergence of the series will be the limit of s sub n as n goes to infinity. Now, to grasp the idea of convergence a little bit better, let's go ahead and look at an example of an infinite series. The sum 1 plus a half plus a quarter and so on and so forth is what we call a geometric sum. And we can rewrite the sum as a series which encapsulates the sequence 1/2 to the nth power from n equals 0 to infinity. Now let's look at the partial sum of this series. S sub 0 is a sum from n equals 0 to n equals 0, which is just the term 1/2 to the 0th power, giving us 1. S sub 1 is a sum from n equals 0 to n equals 1, which is going to be the sum 1/2 to the 0th power plus 1/2 to the 1st power, giving us 1 plus a half, which is 3/2. We can do the same for the S sub 2 partial sum and the S sub 3 partial sum, giving us 7 quarters and 15 eighths respectively. Now you might see a pattern being emerged. We can see that the numerator is always just the next highest power of 2 subtracted by 1. Therefore, for the numerator of the general partial sum, we can plug in 2 raised to the power of n plus 1 minus 1. Now for the denominator, it's even simpler. We can see it's simply 2 raised to the power of whatever the sum is. So for the general partial sum, we can plug in 2 raised to the power of n. Now, if we take the limit of this general partial sum as n goes to infinity, we can go ahead and split up the fraction in this manner, and we say the limit is just equal to 2. In this case, not only have we proven that the sum converges because we can see that the partial sum converges to some finite value being 2, we've also found exactly what the value is. And this is really hard to do for most sums, which is why the geometric sum is very special.